Chapter 9 Kinetic Particle Model of Matter. Index States of Matter, the particle model of matter, structure and behavior of solids, structure and behavior of liquids, structure and behavior of gases, temperature and kinetic energy, Brownian motion, diffusion, gas pressure and molecular collisions, Boyle's law, Charles's law, worked examples, the Kelvin scale, and absolute zero. States of matter, solids, have a definite shape and volume. Their particles are closely packed and held together by strong forces. They are not easily compressed. Liquids have a definite volume but no fixed shape. They take the shape of their container. Their particles are less tightly packed and can move past one another. They are only slightly compressible. Asterisk gases have no fixed shape or volume. They expand to fill any container. Their particles are widely spaced and move randomly at high speeds. They are highly compressible. The particle model of matter. All matter is made up of tiny, continuously moving particles like atoms, molecules, or ions. The interactions between these particles are governed by electric forces. Attractive forces hold the particles together. Repulsive forces prevent them from overlapping. This model explains the three states of matter and the changes between them, such as melting and freezing. Structural behavior of solids, particle arrangement. Particles are tightly packed in a fixed, regular pattern called a lattice structure, with very little space between them. Movement. Particles vibrate in their fixed positions, but do not move from place to place. Forces. Strong intermolecular forces hold the particles together. Density. Solids generally have a high density. Energy. Particles in a solid have low kinetic energy compared to liquids and gases. Structural behavior of liquids, particle arrangement. Particles are closely packed but are not in a fixed pattern and can slide past each other. Movement. Particles move more freely than in solids, with a random but limited motion. Forces. The forces between particles are weaker than in solids, but stronger than in gases. Density. Liquids are usually less dense than solids, but denser than gases and are not easily compressed. Energy. Particles in a liquid have moderate kinetic energy. Structural behavior of gases, particle arrangement. Particles are far apart and randomly arranged. Movement. They move rapidly and randomly in all directions. Forces. The intermolecular forces are very weak or negligible. Shape and volume. Gases have no fixed shape or volume and expand to fill their container. Compressibility. They are highly compressible due to the large spaces between particles. Density. Gases have a very low density. Energy. Particles in a gas have high kinetic energy. Temperature and kinetic energy. Temperature is a measure of the average kinetic energy of the particles in a substance. A higher temperature means more kinetic energy and faster particle motion. When the temperature is lowered, particle motion slows down. At absolute zero, which is negative 273 degrees Celsius or 0 Kelvin, particles have zero kinetic energy and all movement stops. This is the lowest possible temperature. Brownian motion. Significance of Brownian motion. It serves as proof that particles are in motion, even when they are too small to see directly. It strongly supports the kinetic theory and the particle nature of matter. Examples of Brownian motion. Pollen grains moving randomly in water. Dust specks appearing to dance in a sunbeam. Smoke particles jittering in still air. Ink spreading out in water. Brownian motion is the random, zigzag movement of visible particles, like smoke or dust, suspended in a fluid, a liquid, or a gas. This motion is caused by the visible particles being hit by millions of smaller, invisible, fast-moving molecules of the fluid. It provides direct evidence for the kinetic particle model, proving that particles are in constant, random motion. Significance of Brownian motion. It serves as proof that particles are in motion, even when they are too small to see directly. It strongly supports the kinetic theory and the particle nature of matter. Examples of Brownian motion. Pollen grains moving randomly in water. Dust specks appearing to dance in a sunbeam. Smoke particles jittering in still air. Ink spreading out in water. Diffusion. Diffusion is the net movement of particles from a region of higher concentration to a region of lower concentration until they are evenly distributed. Examples include the smell of perfume spreading across a room and a drop of ink spreading through a beaker of water. Asterisk factors affecting diffusion. Temperature. Higher temperatures lead to faster diffusion. Molecular mass. Lighter particles diffuse faster. State of matter. Diffusion is fastest in gases, slower in liquids, and very slow in solids. Gas pressure and molecular collisions. Gas pressure is the result of millions of gas particles constantly colliding with the walls of their container. More energetic particles lead to more forceful collisions, which results in increased pressure. A vacuum is a space from which all air has been removed. Pumping more gas into a container or heating the gas inside will increase its pressure. The pressure of a gas is affected by three key factors. Temperature. A higher temperature gives particles more energy, leading to more frequent and forceful collisions, thus increasing pressure. Volume. A smaller volume forces the particles closer together, causing more frequent collisions with the walls and increasing pressure. Amount of gas. More gas particles in a container mean more collisions and therefore higher pressure. Boyle's law statement. For a fixed mass of gas at a constant temperature, the pressure is inversely proportional to the volume. Mathematically, this can be written as P times V equals a constant. Graph. A graph of pressure versus volume is a curve, while a graph of pressure versus 1 divided by volume is a straight line. Example. When you push the plunger of a syringe, you decrease the volume and the pressure of the gas inside increases. Charles's law statement. For a fixed mass of gas at a constant pressure, the volume is directly proportional to its absolute temperature. Mathematically, this is expressed as V divided by T equals a constant. Practical meaning. Heating a gas causes it to expand. Example. In a hot air balloon, the air inside is heated, causing it to expand. This makes the air inside the balloon less dense than the surrounding air, causing the balloon to rise. The pressure law statement. For a fixed mass of gas at a constant volume, the pressure is directly proportional to its absolute temperature. Mathematically, this is written as P divided by T equals a constant. Practical meaning. Heating a gas in a sealed, rigid container will increase its pressure. Example. If a sealed can is overheated, the pressure inside can rise to a point where the can explodes. Example 1. A bicycle pump contains 50 cubic centimeters of air at 17 degrees Celsius and 1.0 atmosphere of pressure. Find the pressure when the air is compressed to 10 cubic centimeters and its temperature rises to 27 degrees Celsius. Solution. First, convert temperatures to Kelvin. T1 is 290 K and T2 is 300 K. Using the combined gas law, P2 equals P1 times V1 divided by V2 times T2 divided by T1. P2 equals 1 times 50 divided by 10 times 300 divided by 290, which is approximately 5.2 atmospheres. Example 2. A quantity of gas has a volume of 40 cubic centimeters at a pressure of 2.0 times 10 to the power of 5 pascals and a temperature of 27 degrees Celsius. Find its temperature when the volume is 30 cubic centimeters and the pressure is 3.2 times 10 to the power of 5 pascals. Solution. First, convert the initial temperature to Kelvin, which is 300 K. Using the combined gas law rearranged for T2, T2 equals T1 times P2V2 divided by P1V1. T2 equals 300 times 96 divided by 80, which equals 360 Kelvin, or 87 degrees Celsius. Example 3. A fixed mass of gas has a volume of 9 cubic centimeters at a pressure of 1 times 10 to the power of 5 pascals and a temperature of 27 degrees Celsius. Find its pressure when the volume is compressed to 5 cubic centimeters and the temperature rises to 37 degrees Celsius. Solution. First, convert temperatures to Kelvin. T1 is 300 K and T2 is 310 K. Using the combined gas law, P2 equals P1 times V1 divided by V2 times T2 divided by T1. P2 is approximately 1.86 times 10 to the power of 5 pascals. Kelvin scale and absolute zero. The Kelvin scale is an absolute temperature scale that starts at absolute zero, 0 K, the point where all particle motion theoretically ceases. Conversion. To convert from Celsius to Kelvin, you add 273. To convert from Kelvin to Celsius, you subtract 273. For example, 0 degrees Celsius is 273 Kelvin. The Kelvin scale is essential for gas law calculations because it directly reflects the kinetic energy of particles. Thank you for learning with us.